Okay, let's look at this specific logarithmic equation. We've got log base 2 of x plus log base 2 of 2x plus 1 equals 1. And we want to try to find all real solutions. So if you are just interested in looking at what the solution is that I have written out here, that's fine. Pause the video. If you're more interested in a more in-depth explanation about how I came to this specific conclusion that there is only one solution, namely it's -1 plus the square root of 17 all over 4, which if you want to write it out to a few decimal places is 0.7808, and that I'm rejecting the other potential solution that I got, then just keep watching. Okay, so let's get into the strategy and why I'm doing what I'm doing and how do I actually end up with that solution. So I have certain tools for using logarithms, and I want to keep those in mind as I'm trying to think about how to approach the problem. So in this case, I'm looking at just the format of what I'm given. On the left-hand side, I have two logarithms. Yes, they're both the same base, which is great. On the right-hand side, I don't have any logarithms, though. I just have a real number just by itself. So I have two different strategies that I can employ to be able to essentially get rid of the logarithms from the equation and reduce it down to, say, a quadratic or a linear equation, whatever the case may be. So I have to choose, is it more efficient for me to try to get it into the form where I just have one logarithm essentially on the left-hand side equals a number, or should I write a logarithm on the left-hand side equals a logarithm of the same base on the right-hand side? And looking at which of these is, well, closest to what I have that I'm given, it looks like this one is actually the better way to go, right? So how can I actually make these two logarithms be combined into one? And this is where I want to look at the tools up here. So these are the main tools that I have for this specific application. What I'm given is log of something plus log of something. Whenever I have log plus another log and the base is the same, then I can consolidate those into one logarithm. And what the log rule says is that I'm transforming addition outside the logs to multiplication inside the logs. So what I can do is I can start off by just saying, okay, well, let's take this and let's make this one logarithm, but now I have to do inside the logarithm x times the quantity of 2x plus 1. Okay, great. So the first was an application of the first property or the first tool above, or rather tool 1 above. Now that I have it into this format, I want to do some cleanup. So this as is fine, but I know that later on I'm probably going to have to multiply things out anyway. I might as well just do that now. So I'm just going to distribute the x to the 2x and to the plus 1. So I'm really going to have 2x squared plus x inside a log. But again, I still have a logarithm. I haven't gotten rid of the log yet. I have to somehow undo that or transform it into a different type of equation. Now, that means that these three are not necessarily relevant anymore. Right? I don't have two logs anymore, so this is not really useful as a tool at the moment. I don't really have uh, just one exponent which affects every term that's here, right? Yes, the squared is there, but it only affects the x. It doesn't affect everything. So not really applicable in this situation. But what I do have is this. So when we defined say logarithms, when we said like, hey, here's what a logarithm is, we said that you could take an exponential equation and you could reflect it along the line y equals x, and you get essentially a log or a log function. But in doing so, we basically just switch the roles of x and y. So if we start off with an exponential equation, we just switch the roles of x and y. We still have what looks like an exponential equation, just reverse the exponent and the number on the right-hand side. So what we can do is we can actually convert a logarithm, just notationally, this log equation can be converted into an exponential equation. How do I do that? Well, I'm going to start off with a log base, in this case b, and I'm going to zigzag across the equal sign. So I have 2 to the capital N that whatever that real number is, equals A. So here, B to the n equals A. How do I apply that to this situation? What I do is I start off with the base of the logarithm, which is 2, zigzag across, 2 to the first. That's my left-hand side of the equation, and that's going to equal whatever's inside the logarithm, whatever's in the argument. So how did I convert from this log equation to this exponential equation? I used this property up here, like tool number 4. Which is great because now I don't have any logarithms again, but I also don't have any exponentials either, right? The x that what I'm trying to identify in this case is actually in the same level as everything else, right? It's just a plain quadratic equation, and I can use the tools that I have for solving quadratic equations. Now, the first thing I should do is I should move all of the terms over to one side so it looks more typical of how I can use those tools, whether that be factoring or using quadratic equation. And in this case, it's probably a good idea if I just use, well, if I try to factor first, and if I try to factor this, so 0 equals, just by moving the 2 over to the right-hand side, I get -2 as a separate term. So 2x squared plus x minus 2. Right? If I try to factor this, I know I'm going to have 2x and x in the first two slots. But the problem is that I can't really get a positive x in the middle. Right? If we think about this slightly different way, you could try the different combinations here. But just take a glance. So I'm going to have 2 times 1 and 2 times 1. Like I'm looking at the factors of the leading coefficient and the factors of the constant term. I'm not even going to worry about plus or minuses right now, just trying to give an idea. So I can take one of these numbers and one of these numbers, multiply them together, and then do the same thing with the other two. So I can have 4 and 1, and I can also have 2 and 2, right? Because I could multiply 2 times 1 and 2 times 1, like those two. And now the question is, can I add like either 4 and 1 or 2 and 2 by placing, say, positives and negatives anywhere I want to give me just a 1? And it's just not going to happen. If I have 4 and 1, I could get 5, I could get a 3, but that's basically it. I can't get a 1 of that. And then for 2 and 2, I could get 4, I could also get 0. So not really going to work out so well. So let's move on from that. We want to make sure that we can actually get the solution. And it is in the standard quadratic form. So what are we going to look at in this case? I want to identify what A, B, and C are. A specifically is 2. B, although it's not explicitly given, is 1. And C, I'm going to take the negative sign to be part of the value for C. And I'm just going to feed this into the quadratic formula. Right, this will be the catch-all for getting the solution. I know that the quadratic formula has to work for finding a solution to any sort of quadratic equation. So let's just write that down. So negative b plus or minus the square root of b squared minus 4ac. And this is all over 2a. So now it's a matter of just plugging in for a, b, and c. So negative b is negative, and just put this in parentheses because sometimes that does end up being negative. And so I want to show that I'm negating a negative. But in this case, I'm just positive, so it's not a big deal. And then I've got b. So this is 1 squared minus 4 times 2 times -2. And again, this is all over 2 times 2. Great. So let's do a little bit of consolidation here. On the top, I have just -1, but I need to clean up what's going on underneath the radical. So 1 squared is 1, and then I can do the multiplication now. I can either use a calculator, or I could just try to multiply these out together. So 2 times -2 is going to be -4, so that's going to be -4 for those two. And then I have -4 times -4, which gives me a positive 16. But again, if you want to use your calculator because it's more of a fail-safe, then that's fine. Go ahead. All right, so now that I have this, I want to, again, continue to consolidate because I've got two terms underneath the radical. So let's just write that as just 17 over 4. All right, so these are actually two different values. One of the values is -1 plus the square root of 17 over 4. And one of the values is -1 minus the square root of 17 all over 4. So those are both potential solutions. Now, I don't know if they're actual solutions because, well, I need to somehow check to see if they work, right? So the logarithm is not necessarily defined everywhere, so I have to make sure that when I plug something in as a solution, it actually does make sense. Okay, so let's get an approximation for what these values are, and then we can check this out. But I do want to differentiate or distinguish between the two values. So let's do that now. So we have -1 plus or minus the square root of 17 over, or rather, not plus or minus, but rather just plus first over 4. And I also have x equals -1 minus the square root of 17 all over 4. All right, so we will write an approximation for the square root of 17 and then see what we get. Okay, so I've brought up my calculator. And I'm just going to find out what the square root of 17 is approximately. So I'll just do second square root. Your calculator might look a little different. And if I just type this in, I'm just going to get 17. So let's just make sure it's going to output a numerical approximation. I'm just going to put a decimal point there, and then that'll force the calculator to give me some sort of approximation using a decimal representation. So, okay, great. So now I have 4.1231056. And for my intents and purposes, I think it's fine to just go out to 4 decimal places, and then we'll make sure that we're rounding at the end if necessary, right? So in this case, I've got, I don't necessarily want to say equal, but we'll just say it's approximately equal to. It's pretty close, but it won't be exactly equal to. So -1 plus 4.1231, right? So I'm just rounding to the 4th decimal place. And since the position after the 1 there is a 0, I'm not going to round the 2 up or down. Just going to, or not going to round it up, rather. It's just going to stay as is. And this is all over 4. So if I do -1 plus that, that'll reduce it by 1, 2, 3, 1. And this is all over 4. And if I do 3.1231 divided by 4, I will have 0.780. And then I want to go to 4 decimal places. So I've got 7 there. And then the next decimal place is again a 7. So I'm going to round this 7 up to an 8. Right. So that should be sufficient. All right. We'll check this in a minute. Let's do the same for the other value. Right, we already know what the square root of 17 is up to 4 decimal places. So we'll just copy that from above. I want to make sure that I keep this being negative. Again, this is all over 4. So I'm just simplifying the numerators of each of these because I find it to be a little bit easier than having to deal with fractions continually here. If you're fine with doing that, then that's great. So then I have -1 and -4.1231. So this is going to give me -5.1231. And this is all over 4. Okay, so let's type that into the calculator. And we will divide this by 4. We should expect to get a negative answer out of this, and we do. And this is negative 1.280. And then we have 7 as the last place, but the next place is a 7 also. So we're going to round that up to an 8. Okay, brilliant. So let's see which of these two actually makes sense for our solution. And we'll get rid of the calculator now. Okay, so we're focused on these two values, seeing are they both solutions, or is only one solution, or maybe neither of them is a solution. So let's check to see when does our original equation, when does it make sense to plug in here? So if we remember back to the definition of logarithms, the graph of a logarithm is actually only existing when you plug in positive values into the logarithm. So let's recall that log base b or log base 2, let's stick with log base 2 of x, is only defined when x is bigger than 0. So what this means is that if I'm going to expect to have an output here from this value, because remember, this is just some other way when I plug in like a value for x, it's just going to give me some sort of real number value. So if I plug in 1, log base 2 of 1, log base 2 of 2, like it's just representation of some sort of number that's got a decimal approximation. So if my only restriction here is that I have to plug in positive numbers, this is not going to cut it, right? If I plug this value into an expression that looks like this, and you try it on a calculator, it's just going to give you error. So what this means is that I'm going to actually reject this. That can't be a solution. And that's really what I'm checking for when I'm checking solutions to log equations. And the reason why this came up as a potential solution is because when I consolidated these two logs, so here and here, what I ended up with was some sort of quadratic. And that quadratic, right, that made things okay, at least for this step. But we're checking the original. We're not checking this step. We're always going to check back into the original. So what about the other potential solution? And in this case, 0.78, although it's a number that's less than 1, it's still positive. So there's no issue plugging it in here. Is there an issue plugging it in here? So 2 times a number that's slightly bigger than 0, still positive. If you add 1 to it, still positive. So this should be fine. That should be fine if you plug in that value. So no issues there. So this means that there is only one solution. The exact value of which is negative 1 plus the square root of 17 all over 4. But if you just want it up to a few decimal places, you can just write 0.7808. And that is also good enough in this case.